Last chapter, we said a dataset is a shadow of a hidden distribution. Take our running example, a set of house listings, each with a size in square meters, a number of rooms, a distance from the city center, and a price. The distribution behind price tells the whole story. But a shape alone is hard to compare across neighborhoods, models, or time. A distribution is the full landscape of uncertainty. But machine learning often needs a few numbers that summarize that landscape. The first is the expected value, its balance point. Picture a coupon lottery. It pays €0 with probability 0.5, €10 with probability 0.3, and €50 with probability 0.2. The expected value is the probability-weighted sum. E of x equals the sum over every outcome, x of x times p of x equals x. Plugging in our coupon, 0 times 0.5 plus 10 times 0.3 plus 50 times 0.2. Add those terms and E of x equals €13. Not a value the coupon can actually take. It is the long-run average payout if you played this lottery many times. Expected value, variance, and covariance. The same idea extends to continuous variables. Instead of summing over discrete outcomes, we integrate. E of x equals the integral of x times f of x over all x. Consider a regression model's prediction errors, the difference between predicted and actual house price. If we plot their density, a well-behaved model produces errors clustering near zero. For that model, E of error is approximately zero, no systematic bias. It is not perfect on any single house, but it is not consistently over or under price. Contrast that with a biased model whose error density is shifted to the right. Its expected error is clearly not zero. It systematically overpredicts price. Integrals replace sums for continuous variables, but the concept is identical. Expected value is still the weighted center of the distribution. Two models can share the same expected error and still behave completely differently. Model A makes errors of -1, 0, and +1. Model B makes errors of -10, 0, and +10. Both average to 0. But variance, the expected squared distance from the mean, tells them apart. Var of x equals E of open parenthesis x minus mu close parenthesis squared. Equivalently, it is E of x squared minus the square of E of x. Model A's variance is about 0.67, Model B's variance is about 66.7, roughly 100 times larger. Same average error, wildly different reliability. Model A's errors stay close to zero. Model B's error distribution is much wider, so an individual prediction can miss by much more. The mean reveals bias, the variance reveals spread. One catch: variance is measured in squared units. For house prices in euros, variance is in euros squared, a number that is hard to interpret on its own. To fix the units problem, take the square root. Sigma equals the square root of var of x. This is the standard deviation. Suppose our house price model has a prediction error standard deviation of €20,000. That number lives in the same units as price itself, so we can reason about it directly. If those errors are approximately normally distributed, roughly 68% fall within 1 sigma of the mean. With mean error near zero, about 2/3 of predictions then land within plus or minus €20,000 of the true price. Without that bell-shaped assumption, 68% is not guaranteed. Compare interpretability. €20,000 is intuitive. 400 million euros squared, the variance, is not. Standard deviation is what we report to a stakeholder. Variance is what the math prefers to work with. Sigma also sets the scale for standardization. Z equals x minus mu divided by sigma, an idea we will return to shortly. So far, everything described one variable at a time. Now ask, do two variables move together? Covariance answers that. Cov of x, y equals E of x minus mux times y minus muy. Look at house size versus price. As size increases, price tends to increase too. The scatter cloud tilts upward. That is positive covariance. Now look at number of rooms versus distance from the center. In our data, these barely relate to each other. The scatter cloud is a round, shapeless blob. Covariance near zero. Finally, distance from the center versus price. Farther houses tend to be cheaper. The cloud tilts downward. That is negative covariance. One caution: the sign of covariance tells you direction, but its magnitude depends on the units of x and y. A covariance of 5,000 does not mean the same thing for euros times meters as it does for euros times rooms. To compare relationships across different units, divide covariance by the product of the two standard deviations. Cor of x, y equals cov of x, y over sigma x times sigma y. Provided both variables have non-zero spread, correlation sets between -1 and +1. A correlation of +1 means the two variables line up perfectly along an increasing line. A correlation of 0 means no linear relationship. But be careful, x and y can still have a strong curved relationship that correlation misses. Zero correlation does not necessarily mean independence. A correlation of -1 means a perfect decreasing line. As one goes up, the other goes down. Exactly. In our house, data, size, and price correlate strongly, around 0.7, a clear, reusable signal for a model to lean on. Real data sets have many features at once. Instead of one covariance number, we built a covariance matrix, entry I, j equals the covariance between feature I and feature j. Here it is for age, income, and spending score. The same construction applies to size, distance, and price in our housing data. The diagonal holds each feature's own variance. The off-diagonal entries capture how pairs move together. Age and income here correlate positively, while age and spending score barely relate. This matrix is the foundation of principal component analysis. I will explain PCA in details later. Picture a scatter cloud of correlated features. PCA finds the direction along which the data varies the most, the gold arrow through the long axis of the cloud. That direction is the leading eigenvector of the covariance matrix, and it lets us compress many correlated features into a few informative ones, ranked by how much variance each explains. These ideas are not academic exercises. They run through machine learning end to end. Under squared error loss, the expected value is the best single prediction. Predicting the conditional mean minimizes expected squared error. That is why regression models trained with mean squared error learn averages. The variance of a model's errors tells you whether those errors are tightly clustered or dangerously scattered, even at the same average error. Standardization, z equals x minus mu over sigma, centers features and puts their spread on a comparable scale before training. The covariance matrix drives PCA and other dimensionality reduction methods. Distance from the mean measured in standard deviations flags anomalies, and combining variances and covariances of individual assets gives you the variance of a whole portfolio, the same math behind financial risk models. Back to our house price story. E of price is the mean price. var of price measures how widely prices vary, while sigma of prediction error expresses the model's typical error scale in euros. Covariance tells us that size and price move together, and correlation gives that linear relationship a unit-free strength. A distribution is the full landscape. Expected value marks its balance point. Variance and standard deviation describe its width. Covariance and correlation reveal how two variables move across it together. These summaries give machine learning numbers it can compare, standardize, and act on. Next chapter, we ask why more data helps. We will meet the law of large numbers and the central limit theorem, two ideas that explain why averages stabilize and why sampling distributions become predictable. Thank you for watching, stay curious, and keep turning distributions into numbers you can trust.